Okay. Let's start. This is the last piece of Riemannian geometry, actually differential geometry. It's not Riemannian at this point. We need to introduce. We would like to introduce, and nothing is needed. The reason is at least twofold. One of the reasons will be that it will give us a nicer geodesic equation, which is actually used in computing geodesics. The other reason is that it is, in general, a convenient framework for some information geometry problems. We haven't really dealt with information geometry apart from 2-3 lectures, but we will talk about it a bit in the last 2 hours. So we will be talking about Hamiltonian dynamics or Hamiltonian equations or Hamiltonian flows or whatever you want to call them. If you ever studied, well, mathematical physics or mechanics, rational mechanics, things like that, you know that there is the Lagrangian formalism and the Hamiltonian formalism, and in between them there is this weird Legendre transform. This setting can be, well, transposed, but actually, I mean, it makes sense also on manifolds. Actually, it makes sense mainly on manifolds, at least from my viewpoint. We won't be using the full generality possible, just because in this course I have never talked about general differential forms. So we cannot take the route of, well, I will just give you the names, symplectic manifolds and the symplectic structure on the cotangent bundle and stuff like that. But that would be the natural setting for the Hamiltonian formalism. Anyway, we start from something called fiber derivative, which is actually a very easy idea. So we have a manifold, M, and a smooth function from the tangent bundle of M to R, the Lagrangian. I mean, the Lagrangian takes, I mean, the time-independent Lagrangian takes as an input space, position and velocity. Position is a point on your manifold, and velocity is a tangent vector on your manifold. So it takes as an input a point and a tangent vector to that point. So it takes as an input an element of the tangent space. So the tangent space is our phase space in the sense of physics. Obviously, you can also define something, I mean, once you give a curve inside your manifold, you can also define a Lagrangian which depends on time, but in general you will have something, for example, the usual things like a free particle moving on the tangent, free particle Lagrangian. So the free particle, I mean, my physics is quite rusty, but anyway, the free particle Lagrangian is easy, and it's just the kinetic energy. So the Lagrangian in this case is just this one, okay? So if you write L as L of X and V. Obviously, we need a metric to write this. So we need the scalar product and the tangent because we need to have the norm of a tangent vector. So on a Riemannian manifold Mg, we can consider the Lagrangian of X V given by 1/2. Well, M is a constant. We can always set M equal 1. Now, and if there were any physics or students of physics in the audience, they would probably gasp because M should be dimensional, but we are not doing physics here, so M is just a number. Anyway, 1/2 of the norm of the velocity part, so 1/2 of Gij Vi Vj. And if you think, I mean, what would you expect the trajectories of a particle to be under this kind of Lagrangian? Well, they will be the zero velocity. But if the particle is moving, you will get the shortest path. So this gives geodesics. We already know that, we already wrote it down, and you can derive it by minimizing by showing that minimizing the length implies minimizing the energy function. So the action is the energy functional, and the energy is just the integral of this thing. So the Lagrangian is just this thing. But anyway, so this is a function in general from the tangent bundle to R. The fiber derivative of such a function is the map from the tangent to the cotangent, such that for each point in M, the fiber derivative of L at that point, which goes from the tangent to that point to the cotangent to that point, sends a tangent vector to the differential of, well, this would be the other L, of L of X at V. So what we are saying here is that L is defined from Tm to R, so we can interpret it as a collection of functions depending on X from Txm to R. So it's a smooth collection of functions from tangent planes, tangent spaces to R. The fiber derivative at a point X is just the at the vector V, the differential of Lx at V. So Lx is a function from a, this is some kind of, this is Rn, once you choose a basis. So Lx is a function from Rn to R. Its differential at every point gives an element of the cotangent space to Rn, so the differential forms. Of the dual of Rn, so the cotangent space to M. Now, in local coordinates, this means that the differential, the fiber derivative of L at the point x at the vector v is just the derivative, the partial derivative of Lx of v with respect to Vj, because remember, Txm is just a vector space, so this vector field is just the partial derivative with respect to Vj, which is a global coordinate on the vector part. So it's the partial derivative with respect to Vj of Lx of v times dxj. This is the tool that generalizes the Legendre transform to manifolds. So if our function L is convex, which in this setting means that Lx is convex on every tangent space with uniform bounds on your manifold, on the, for example, Hessian matrix or something like that. Here, we can say convex here because convex, we are just requiring it on the tangent space, so is the usual concept of convexity. So the matrix of the second derivatives is positive definite. This makes sense because Txm for every x is a vector space. So, and we don't want a given bound on the eigenvalues of the Hessian, but just some bound to be uniform. So it has to be separated from zero in a nice way on the manifold, but we don't care how much. So changing coordinates will not affect that. If the infimum of the Hessian matrix on the whole manifold is not degenerate, it will not be changing coordinates. And superlinear, that is, this kind of inequality holds uniformly on the manifold again. Then, if these two conditions are true, dfL, the fiber derivative of L, is a diffeomorphism. So, well, it sends a tangent space to the corresponding cotangent space. So it doesn't mix up the axes, the points on the manifold. So x is always injectively mapped to itself. The whole point is that fiber-wise, on each tangent space, from each tangent to each cotangent, so as a map from Rn to Rn, this is invertible or not. In the case these two conditions hold, the function is invertible and the inverse is smooth. We need uniform bounds so that the inverse is smooth. But anyway, now we can give two definitions. Well, the energy function of L is just the fiber derivative, which is, this part here, the fiber derivative of L applied to xv is a map from the tangent to the cotangent, so this gives a differential form at x. So this gives a cotangent vector, so an element of the dual of the tangent. So this is a differential form evaluated at x, applied to v, minus L. Well, this L should be again L. Minus L. Now, the Legendre transform is L star. We will be briefly using star, but because, I mean, we have too many stars things in this lecture, so, but the usual symbol is the star also for the Legendre transform. And L star is the energy composed with the inverse of the fiber derivative. Now, this starts to look like the Legendre transform you know, because the Legendre transform you know is, well, x times p minus the function, and you want to optimize this functional. And this is the actual form of the optimization in this case. But anyway, what happens in coordinates? If we take a point in M and two tangent vectors, so this part here again is a cotangent vector because it's the image through the Legendre transform of the fiber derivative of xv. So this part is a cotangent vector. So if you vary x, you will get a differential form, and it's applied to a vector v again. The result is that you are multiplying the jth derivative of Lxv with respect to the variables v, so the jth derivative of velocity of the Lagrangian, times the jth component of the other tangent vector. So the energy is, well, I've just written out this explicitly, is the partial derivative with respect to Vj of L times Vj, because the energy is applying these cotangent vector to the vector V itself, so it's times Vj minus L. And now if x alpha is the image of xv, the Legendre transform, which is defined on the cotangent space of x alpha, is alpha j vj, so the usual product between form and vector field, minus L of xv, where xv is the pre-image of x alpha. So it doesn't get any simpler than the Legendre transform on Rn, but it's not much more complicated because in the end, in coordinates, you are having exactly the same expression. And you can prove that in suitable local coordinates, you are actually doing the Legendre transform. So anyway, the Legendre transform in the end takes some function from the tangent space to R and gives you a natural way to associate to it a function from the cotangent space to R with some properties. Now, if you take a convex and superlinear Lagrangian, which is usually the case, because because of how energy is usually, the energy functional usually written in physics, its Legendre transform is usually denoted by H and called Hamiltonian. So the Hamiltonian is something which is like the Lagrangian for position and velocity, just it uses position and the cotangent vector. Now, the cotangent vector in physics is given the meaning of momentum. For us, it's just a cotangent vector, but usually in physics it's called momentum. By the way, the usual symbols in physics are weird, like they use weird. They use Q dot for the velocity and P for the momentum. We will be using X, V, and alpha because dots mean something else for us, but I mean, everything is equivalent, obviously. Now, with Lagrangian, you usually end up writing down the Euler-Lagrange equations for the functional. Euler-Lagrange equations give a geometric flow on the tangent space. Why? Because the equations for the Lagrangian can be written like this. X dot is V, and V dot is some vector field. How is written the vector field? The vector is written like that. It is a matrix times the space derivative of the Lagrangian minus a matrix times the second derivative mixed, one in velocity, one in space of the Lagrangian times the velocity. So if you write, I mean, this is exactly Euler-Lagrange equation, and it's easy to see it because let's see. You want something like the dt of the velocity derivative equals space derivative. Now, you can just apply the, I mean, this is a function of x and v, so you are taking the vi, vj, l, v dot I, plus xi, vj, l times x dot I. And this should be equal to dxjl. Now, this is vi, and if you call this matrix mij and construct the matrix m ki, whatever, it's symmetric, mik such that, which is the inverse, so such that m ik m ij is equal to delta kj, then you can write everything as v dot I equals m yeah, I mean jk, but anyway. dxjl minus mjk dxi dvj l times vi. So this is exactly the Euler-Lagrange equation, just twisted a bit. And obviously, the other equation of the pair is that I mean, how the x and the v variable relate, so that the time derivative of the x variable is the v variable. So this is the Euler-Lagrange equations, which, if you look at them this way, it's the equation for the integral curve of a vector field. It's the equation for the flow of a vector field, because we have a point in the tangent space is position velocity, xv, and we are saying that the time derivative, so we are given a curve, and we are saying that the time derivative of the x part should be the v part, and the time derivative of the v part should be this expression. So it's just a vector field. So this part here is just a vector field, which is the v vector field and this other vector field. So the Euler Lagrange equations give you a flow on the tangent space, which is called Lagrangian dynamics. I mean, obviously, one equation of the flow, I mean, this is just a very complicated way to think about it, because in the end, one equation of the flow is just that is a trick to write a first-order equation instead of the second-order equation, no? So it's the usual trick. When you have a second-order equation, you can try and write a first-order one by adding a variable, whose derivative will be the second derivative of your variable. So this is actually a second-order equation in x, but we are introducing v, which is the first derivative of x, and so everything works. Anyway, this is called the Lagrangian vector field. This weird thing here. And I mean, usually you don't read this formulation because it's cumbersome, because this vector field is quite complicated to write down. I mean, the inverse of the matrix this is by the way, this is the Hessian of L restricted to the tangent space. So this is why we were talking about fiber derivatives, and we gave the convex definition, which is just convex on every tangent space, because we need this matrix to be invertible, and if the function is convex, the Hessian is surely invertible. By convex, I always mean strictly convex here, so Hessian positive definite. Now, if you apply the Legendre transform to everything, you get, well, obviously x stays x, v becomes alpha, so a cotangent vector, so x dot alpha dot equals what? Well, you end up with these two components, which are the alpha derivative of h, so obviously I mean that x dot, the jth component here will be the jth component here, and the jth component here will be the jth component here. So these are the derivatives with respect to the alpha variables, so the moments, the momentums, the momenta. I don't know how you're supposed to construct the plural here. And correct one would be momenta, but anyway. And here you get minus the space derivative of h. This is just, I mean, you take this geometric flow coming from the Lagrangian equations, which is a bit involved. You apply the Legendre transform to everything, and you obtain this much simpler version. And this is usually called the Hamiltonian vector field. And these are the equations of the Hamiltonian dynamics or the Hamiltonian flow on the cotangent space, which are equivalent to the Lagrangian ones. Now, example, the geodesic equation. Let's do computations a bit, so maybe we understand something. The Lagrangian for the geodesics is the kinetic energy. We saw it before. So 1/2 GIJ VI VJ. So so this is just, I mean, if you fix x, this is V transpose GV with G asymmetric matrix, okay? 1/2 of this. So the derivative of this in the V variables is easy. It's just G times V. So if you have the function that goes, that sends x to x transpose AX from Rn to R. In our case, we also have the A is equal to A transpose. And this map is called L. Then the derivative of L applied to a vector y at the point x is just 1/2 of this, sorry, x transpose AY. This works because A is symmetric, so otherwise you will get two terms which are different, but in this case they sum up to x transpose AY. So in our case, the fiber derivative is just Gij Vi Wj. So, x alpha, so position momentum, is equal to the fiber derivative of L applied to position velocity if and only if alpha I is equal Gij Vj. Because this is this cotangent vector applied to W, and you can clearly see that the coefficient of the cotangent vector should be this part here. So, in this case, the fiber derivative is just lowering the index. So the Legendre transform is just lowering the index minus the Legendre transform is just the scalar product minus the function, which is exactly how, which is the Euclidean Legendre transform. Okay. So if you write the Legendre transform out here, you get what? You get the scalar product between alpha and V. Alpha applied to V, but alpha is lowering index of V, so is V scalar product V minus the function, which is exactly the minimum of the function that defines the Legendre transform in the Euclidean setting. Anyway, you do all the computations, and which are not too many, and you end up with this expression for the Hamiltonian. So the Hamiltonian is just the Lagrangian with switched indexes. This happens just here. It's not a general rule, but in this case, it's very simple. Now, the derivative of the space part is the derivative. The time derivative of the space part, of the space variable, is the momentum derivative of the Hamiltonian. If you derive this Hamiltonian in alpha I, or alpha j, whatever you want, it is the same, it's symmetric. What you is the same computation we did before on this other thing, and so you get Gij alpha j. But if you think about it, Gij alpha j is Vi, because here you're raising an index on alpha j, so you get Vi back. And so you are just writing that the time derivative of your position is the velocity, which makes sense. The second equation is that alpha dot I is so the derivative of the momentum variable coordinate is minus 1/2 of the ith space derivative. So I should write it. So this is dxi of the norm of the norm of your momentum. Now, why is this interesting? Because the Euler-Lagrange equation for geodesics involved second derivatives of the Lagrangian. Even if you wrote it down as a first-order differential equation for x and v, it involved taking second derivatives of the Lagrangian, so it involved taking second derivatives of the metric. This formulation takes only first derivatives of the metric, of the Hamiltonian and hence the metric. So this is easier to compute. Obviously, as differential equations in x and v, x and alpha, they are completely equivalent, so they are both systems of first-order differential equations. But the coefficients involved, in one case, are second-order derivatives of a functional which involves the metric, and here are first-order derivatives of a functional which involves the inverse of the metric. So if you do all the steps in between, they are indeed equivalent. But from a computational point of view, second derivatives and first derivatives are not the same. And if you have some reasons for which the inverse metric, so the Gij with upper indices, you have a closed form for it, it's easy to compute or something like that, then it's easier to go down this way instead of the Euler-Lagrange equations, if you want to actually compute a geodesics. And this is what I'm saying right now. So you can use this to solve your first order differential equation. For example, by a Runge-Kutta method. So usually you use just an order 2 Runge-Kutta. So you just you want to make a step of length epsilon, and you just update everything at epsilon halves. It's actually just like this. And this would give you an accuracy of epsilon squared on the result. So, and you can do this because in the end, when you're updating your method, you are just taking first derivatives of a function which depends on Gij and your alpha E alpha j. Space derivatives, but anyway. Estimating as a minimum energy path the optimal deformation between two images. We will talk about it in the end of the next hour. Geodesic regression. So you can use this characterization of geodesics to write the equivalent of linear regression on manifolds, which is called geodesic regression. So you want to find the geodesic that fits your data at best. And the usual way of doing this is exactly to use as a characterization of the geodesic the Hamiltonian equation and Hamiltonian Monte Carlo method. We'll talk about it later on. Now, the last note I want to make is a bit more on the theory side. So we saw that the Hamiltonian equations could be expressed, it was not that useful, but to fix ideas, as a flow on the cotangent space whose infinitesimal generator, whose vector field was x sub h, and had an expression involving the first derivatives of the scalar function h. So it's tremendously close to a gradient descent. A gradient descent is, you have a map F from your manifold to R, you define a vector field x of F, and you just want to solve this differential equation. Well, minus. Plus, minus. You can reverse the direction you are following the curve. So this is just gradient descent, because if we select the right vector field, this is gradient descent when we set x of f equal to grad f, which is just the differential of f with a raised index. So we use the metric to transform the differential of f, which is a differential form, into a vector field. So in coordinates, we are just raising the index of the differential form. So this is just it. And what do we get here? Well, we get the not the local, at least a local minimum point of f, because following the gradient backwards, we get a curve which goes towards, hopefully, a minimum point, or at least a critical point of our function f. So this is, I mean, I don't know if I ever said this, but the gradient descent can be seen as the discrete version of following the flow of the gradient vector field. So now, also in the setting of Hamiltonian and Lagrangian, we are trying to minimize things. We are trying to find optimal things. We are trying to minimize energy for the Lagrangian. For Lagrangian, the vector field is complicated. If you remember, I mean, there were like the inverse of the Hessian metrics in the velocity coordinates and the mixed second derivatives space velocity. So it was a mess. The infinitesimal generator of the Hamiltonian flow is easier because it's just the momenta derivative and minus the space derivatives. It looks like a gradient, more or less. It's not. But it would be nice to obtain this vector field as a function of the differential. The usual problem is that the vector field is in the tangent and the differential is in the cotangent. This time in the tangent and the cotangent of the cotangent, but it's always the same thing. I mean, look back at when we discussed this problem when we introduce the metric, but it's always the same thing. So the vector field and the differential form. They are in two spaces which are one dual of the other. The usual solution is we need an isomorphism between the tangent and the cotangent. That is, usually we need a non-degenerate bilinear form on either of them. The metric is a non-degenerate symmetric bilinear form on well, positive, not only non-degenerate, positive, on the tangent. So, well, we could also give, you obviously know that, the metric on the cotangent, which is the dual or the inverse metric, and this would be the same thing. So usually you assign this bilinear form on the tangent. Now, the usual definition is the following. So, how does this work? You have this bilinear form omega. So this is a thing that goes from the tangent at a point. So omega at a point is the tangent at the point of the cotangent times the tangent at the same point of the cotangent, and gives you a number. So if you have a vector field on the cotangent, how do you use omega to transfer x to a differential form? Well, you define, well, this is the differential form. So you obtain alpha in the differential forms on the cotangent space as alpha of y equals omega. Well, here depends, I mean, let's stick to the first coordinate, because we didn't say it's symmetric. I don't know if it won't be. So this is the usual definition. Now, so if the differential of your function h corresponds to a vector field x of h, this means that applying dh to x of h should give you this. But in local coordinates, dh is, well, the space derivatives of h times dx plus the momental derivatives of h times the alpha. I'm writing these meaning that it will be dxi times, so the partial derivative in xi times dxi, the partial derivative in alpha I times the alpha I, etc. Whereas h, what is it? Is the alpha derivatives times dx minus the x derivatives times partial alpha. So you can clearly see that if you pair these, if you apply this form to this vector field, and you don't need any bilinear thing to do that. I mean, you just pair the vector field with the form. So partial x eats up, so dx eats up partial x, and d alpha eats up partial alpha, and you end up with 0. Okay. So you end up that with dh applied to x, h equals 0, which is a feature of the Hamiltonian dynamics. I mean, it's not a chance. So that means that this omega xh should be 0, which means that our form cannot be symmetric if we want it to be non-degenerate. Because if it's symmetric, omega xx is positive, or 0 if x is in the kernel. We want it non-degenerate, so no kernel, so it cannot be symmetric. Actually, it will have to be skew-symmetric. So it will be represented by skew-symmetric matrix. And this is the matrix. I mean, quite easily, this is the matrix. It is a block matrix, n times n, 2n times 2n, and identities are the n-dimensional identity matrices. So if you denote by J also the global isomorphism between the tangent and the cotangent, your Hamiltonian equation becomes the x dot alpha dot equals J applied to the differential of H. So you get also the omega, which is given by the same matrix, and the pair cotangent space omega is called symplectic manifold. I don't care about, I'm just giving you the name in case some of you heard about that or whatever, but this is the, so this is just the starting of the more theoretical explanation of the Hamiltonian dynamics. But the main point here is that we have a bilinear symmetric form, omega, which is called symplectic form, but who cares, which is skew-symmetric, but which nonetheless is non-degenerate, so it will give you a pairing between tangent and cotangent, an isomorphism between tangent and cotangent. So it will transform the differential of the Hamiltonian function into some vector field, and this vector field will give you the Hamiltonian flow. So it works more or less like the gradient descent. So it's actually a minimization of something. Also, usually the Lagrangian is the difference between the kinetic and the potential energy. The Hamiltonian turns out to be the sum of the kinetic and the potential energy. So you're actually minimizing the Hamiltonian when you are minimizing energy. So it makes sense that we are in some way following the differential of the Hamiltonian. So the gradient flow, it's not a gradient flow, but the flow we are following is something which is more or less a gradient flow for the Hamiltonian. It's built up with the partial derivatives of the Hamiltonian. as opposed to the Lagrangian, which is easier to deduce, but which gives you much more complicated and less intuitive equations. And I think it's more than enough about this.